So from last lecture, we stopped here. We were talking about Hermitian matrix. Do you still remember what is Hermitian matrix? Yeah. So it is a matrix that equals to its self-adjoint dagger, right? So what is dagger? What is self-adjoint? How do you operate? It's just like the dual space. Yeah, say again. Transpose and conjugate, right? Sometimes complex conjugate. Yeah, sometimes if you forgot that, it's a good guess if you don't have choice, right? It must be something to do with transpose and conjugate. So we say that what is a measurement? So in a measurement, you always get some value, right? Like the spin plus half or minus half. It turned out this value are the eigenvalue of a certain matrix. And so we say that the observable or the measurement correspond to a matrix. But this matrix must be Hermitian. Why? Because what type of eigenvalues does it have? Yeah, Hermitian matrix has real eigenvalue, right? Even you don't know how to prove it, right? In my book, you can see how to prove it or just Google. But you should always remember, whenever people talk about Hermitian matrix, the first thing is this equation. The second thing is that it has real eigenvalues, right? So every measurement, for example, I measure the spin of an electron. It corresponds to a Hermitian matrix of this form. And the value I'm going to get are the eigenvalues of this Hermitian matrix. But don't get confused. It doesn't mean that the measurement process is the application of the Hermitian matrix. No, we don't do that, right? Because there's a wave function collapse in every measurement. It just say that the eigenvalue correspond to a certain Hermitian matrix. That is the first thing. Is this okay? Yeah. And then we try to review something. For example, I have this general state of 1 qubit alpha spin up plus beta spin down. I can call it alpha half, beta negative half. It doesn't matter because it indicates that the eigenvalue is half for spin up, eigenvalue of spin down is negative half. Okay? I say, what is the probability that I will measure spin up is alpha square. We remember that, right? The magnitude square. And the probability of spin down is beta square. So here we learn another thing is that you actually can find out the probability by using the so-called projection operator. Okay? We find the expectation value of the projection operator. Then we will be able to find the probability. So you still don't know what it is? What we want to do is to understand what is projection operator, which is a very important operator. And as its name implies, you probably can understand, I stand here, if the sunlight shining on my left, then you project myself to the wall on the right. That is the projection. So you can imagine projection, if you project in the right way, you will get different components in the basis, right? So let's think about this. So we say projection operator, usually you need to say of what, okay? Of a particular vector, okay? We say we try to project something related to this V. Then we write it as what? The outer product of V. This is an operator, right? We have learned about scalar, we learn about vector, right? We also learn about matrix. Two vector, outer product. This is cat, this is bra, right? Do not confuse with this. What is this? What does it give us? Bra times cat give us what? Scalar, matrix, or scalar. Vector? Scalar, right? So this is the inner product. This is the inner product, right? But the outer product is what? Cat times bra. And it's very easy to see. For example, if I say the V I'm interested in is 0. Let's say V is just 0, one of the basis vector. Then it is 1, 0 in column form. Right? Then what is the projection operator of 0? Then it will be the outer product of 0, which is 1, 0, which is the cat times the bra. Right? So again, this is the cat, this is the bra. You go through the matrix multiplication. I hope that you can practice. Don't mess this up. Row times column give you this one. Row times column give you this one. This row times column give you this one. This row times column give you this one. So you get this 1, 0, 0 matrix, 1, 0, 0, 0 matrix, right? And this is the projection operator. Is this clear? Any questions? So what is the use, right? You probably will think maybe I try to use this one on a vector. Is it going to do some projection? Let's see if that is the case. For example, let's say I have a general vector alpha 0 plus beta 1. I apply the projection operator of 0 to it. This is an operation. Right? When we read this, you probably understand it's a matrix times a vector. Right? But in higher level, you just think I have an operation applied to a vector. I even don't need to know the matrix form, the element. But this is the meaning of it. I apply an operation to a vector. Right? Of course, we need to go to the matrix form. Right? But here, actually, we don't have to. So we say this is 0. This is the projection operator, right? I apply this to psi, which is alpha 0 plus beta 1. You might get confused, but again, just like the elementary school student we have mentioned, if we just treat it as a regular distribution rule, right? A regular multiplication and addition, you apply the distribution rule. If this is a product, outer product, isn't that I can apply this to alpha 0, 0, 0 plus beta 0, 0, 1. Do you see what I'm doing? The whole thing just go in and I get this. Right? When you're very familiar with this, you don't need this intermediate step. But from here, do you see that? Is that okay? And we also agree that it followed the associative rule. We did not mention that, but now just tell you that it followed the associative rule. What is 0? Although this is, look at this is outer product of 0, right? But then you multiply by a cat. So I can say that, let me first to do this operation. What is this operation? Huh? Someone just say something. Inner product, right? Because this is the bra, this is the bra, and this is the cat. Make sense? So what is the value of this inner product? What is 0 inner product 0? 1, because we assume it's normal. That's now you see orthonormal basis is so important. Make things much easier. What is inner product of 0 and 1? 0, thank you. So the second term is gone, right? So because of this, I get alpha 0. So do you see what are we doing? This projection operator applied to this guy, it gives me the components of 0. And that's it. That's why it's the projection operator. Make sense? So now you trust me. If I have another vector, might not be 0, 1, just generalized vector. Projection operator will extract the parts that it overlap with it. So instead of standing here, if I want to know my component on this table, I just shine the light on me, I get the shadow. That is my component, right? I can project to this screen, or then project to your body, your 45 degree or whatever. I use the correct projection vector. Then I will get how much of me containing that component. Okay? Now, that is the first thing. What I get is a vector here. Another thing is that what we discussed earlier, what if I put psi also on the left, right? It's a little bit complicated, but just look at this. This is a vector. This is operator. Operator on vector, what do you get again? What do you get? Scalar, vector, or matrix? Vector, right? Because matrix times vector. So this is a vector. It's a cat. And what is this? This is bra. I'm doing an inner product of a bra and a cat, right? Although the cat is actually another cat after some transformation, right? So I will continue with this then. How do I write the bra form of the psi? Can someone tell me? This is the cat of psi. Alpha 0 plus beta 1. What is the bra form of psi? Again? Someone say alpha. I try to do the bracket notation. So you need to make this as bra, right? Is this correct? Excellent. You need to have a complex conjugate. Don't forget this. But these are all just simple rules. You just need to follow the rules. And then the whole thing multiplied by alpha 0. Why I do alpha 0? Because I just got from here alpha 0 is projection operator on psi, right? P psi. So let's do the same thing again. This is equals to alpha star 0. Let me just put alpha. I put all the scalar at the beginning. 0, 0 plus beta star alpha 1, 0. Am I correct? Yeah. What is this? 0 inner product 0. 1. 1 inner product 0. 0. Right? You see this very often, right? I know some of you feel very bored, but this is important. Equal alpha star alpha, which is equal to alpha magnitude square. And what is this we just said? Thank you. This is just the probability of measuring up. Here I just call it 0, right? So what have we learned? We learned the definition of projection operator. Very easy. Just outer product of that corresponding vector. Right? Even you don't understand, don't mess this up. Outer product. Don't mess up. Put in cheat sheet. Yeah, your exam allowed to have a cheat sheet. Right? This is first thing. Don't mess up. Don't make it inner product. Right? I cannot let you pass if you mess this up. Right? Put in cheat sheet. This is what you learn. Even you don't understand. Second, you realize that this projection operator is a matrix. You apply to any other vector, you find the component from that vector that equals to this corresponding vector. I mean, how much of this vector does this one contain? Right? How much portion? That's first thing. And last thing is, if you want to find the probability of getting a certain state, you just get the projection vector of that state upon measurement, right? Certain state upon measurement. You just get a projection operator and do this operation. This operation is what? This is actually the so-called expectation value of P, right, on psi. So we did not talk about expectation value. I assume you know already. Did we talk about this? I get confused because I'm reviewing my book and then I don't know where we are. So did we talk about this expectation value so far? That's last year. No, right? So it was like in E225 or E1636 161, right? But anyway, what is the meaning of expectation value? You have an operator, and then I have a state. I want to know if I do the measurement of this state, what is the average outcome I can have? Okay, so this is how you find the expectation value. We will go through this later again. But in summary, this is what we say. The probability, right, of finding a state in a I state is just equal to this one. Okay? So if you still feel a little bit confusing, just remember these 3 points I just said. And we are going to keep using this. We will come back again. Okay, any questions? If no, then here, oh, now I know. Yeah, I get messed up. Just say again, what is the meaning of the expectation value, right? So I don't want to write it just to save time. Let me ask you, if I want to say, I do a measurement, remember, this is the matrix. A is the Hermitian matrix corresponding to a measurement. This is a very important concept. We're saying that, okay, we're doing a certain measurement and it has a certain Hermitian matrix. We do not use this matrix to do measurement. Remember that. It's not a quantum gate, okay? But the measurement corresponds to this matrix. And it has some eigenvalue, right? Its eigenvalue, maybe I don't write in this way. It has the, and this one has the eigenstates of 0 and 1, for example. And it has the eigenvalues of lambda 0 and lambda 1, which can be, for example, 1/2 and negative 1/2. Make sense? I do measurement, right? So you go to do a measurement. You measure many times. Sometimes you get 1/2. Sometimes you get negative 1/2. You may have a higher chance to get 1/2 or higher chance to get negative 1/2. Depends on the state of your system. You take them, and then what do? You can find the average, right? So what is the average? Of course, the average must be equal to the probability of measuring 0 times the value you get, plus the probability of measuring 1 times the value you get, right? For example, you have 10% of probability getting half, and 90% of probability getting negative half. Then the average value is 10% times half, and then plus negative 90% times negative half, right? Then, correct? This is how you find the average value, right? So then, good. Now, and then I just told you, the probability of getting 0 is just equal to this expression, right? You sandwich the state to P0, okay? The probability of getting 1 is just this 1, but this one is P1, the projection operator to 1. And again, what is projection operator to 0? It's just the outer product of 0. So now you see the beauty of bracket notation. This looks complicated, but I can just insert this as outer product. And then you can group them together if you want. Associative rule. Same for 1, you get 1, 1, right? So now this one, I then factorize it. What do I factorize? This is a plus, right? I just use what you usually do. This is multiplication, inner product. So I take out this side to the left. So this one go out, this one go out becomes this. This is also inner product. I take this to the right. This one go to here, this one go to here. Very confusing. Then I have this, or right? I have this, still have 0, 0 side, lambda 0, 1, 1 side, lambda 1, that I put here. Right? And this one turned out to be A. Why? Because A, if you go through the calculation, you see that this one is A. Because 0, 0, as we just calculated earlier, equal to 1, 0, 0, 0. If you repeat with 1, 1 outer product, what you get is 0, 0, 1. So basically, this is this matrix times lambda. And then this is this matrix times the lambda 1. This is lambda 0. You add them together, it becomes this. Right? So we will not go into this detail. You do need to already know some of this. But if you don't understand, email me or come to the tutorial. Here is just a basic overview. I try not to have this type of derivation or proof in the exam, so don't worry too much. But we will have this a lot in the homework, so you can ask ChatGPT or wherever, discuss and make sure you understand. Okay, but the final message is that this one is the expectation value of A for this state. This is a little bit too much, right? But you see, I keep repeating. Later, we are going to repeat this concept again. I want this night. So that's why you watch the video or come to the class every day is very important. Okay? So
I feel silly for this.
Yeah.
How do you differentiate ship matrix?
My emphasis is just saying that Hermitian matrix can be a gate. I do not say Hermitian is not a gate. What I'm trying to say is that when we talk about measurement, the corresponding Hermitian matrix is not the operation for you to do the measurement. Right? For example, sigma c. You measure the spin. You don't have any physical operation called sigma c to measure it. It's just that when you measure the spin, it collapses. The eigenvalue correspond to the measurement value correspond to the eigenvalue of sigma c. And sigma c is this corresponding observable matrix.
Okay. Well, I don't know. You just said earlier that it's something.
Yeah, sorry, that confused you. It can be a gate for Hermitian matrix, but not in this case when we are doing measurement. Right? Good point. Yeah.
So is it a procedure to obtain the eigenvalue?
No, it's the procedure to find the expectation value, which is the mean of the measurement. Yeah. Assume that you already know the eigenvalues.